So we're going to look today at many body problems. Problems when there's more than one mass, usually attached by strings. And what I said to you last year was we can actually just slightly modify our tug-of-war winner minus loser approach, and then we can still do this the same way. So I wrote down here, in these problems we have several objects connected together by strings or ropes. And the easy approach is to realize that we can treat the system as a single object since all parts are accelerating at the same rate. Sorry for those of you who are watching on YouTube, but those of you who are in class, here's my argument. Here I have two objects attached by a string. Even though they're accelerating in different directions, if the ball on my right, your left, is accelerating at 2 meters per second squared, this hanging mass is also accelerating at 2 meters per second squared. They're going to have the same acceleration. Alice, what we're not going to let you do is, believe it or not, in physics, it's called a jerk. We're not going to let you do that. That there, the physics of that is terribly difficult. It's a fourth order derivative for those of you that have done calculus. And it's not an easy thing to study, as a matter of fact. Later on this year, I'll talk a little bit about jerks, the physics concept, not the human beings. And we'll realize it's very difficult to come up with an experiment that only has jerk and doesn't also have acceleration. And so it's a tricky thing to study. Point being, well, all of our accelerations, if they're attached by ropes, are going to be smooth, and you can assume both objects have the same acceleration. So, by the way, there is another method, and you were doing that in summer school, you told me. The other method is to write an equation for each mass's tension, realize that the tensions are equal to each other, and you create a system of equations, and you can solve for T or you can solve for stuff. And that's how I was taught, Maddie, and it's perfectly acceptable. And for my new students, you may do it that way, and if you're more comfortable with it, I'm totally fine with that. I think this method, though, is a little cleaner. So example number 1 says, there we go, find A, the acceleration, and B, string tensions. Okay. Madison, what does this want me to find? And? How am I going to start? You know, this is a good job for. Now, how do I know that? Well, they're asking me to find more than one thing and there's more than one mass. I should get organized. I usually do my free body diagram starting on the left and going to the right. You don't have to, but if you want your mass numbers to match my mass numbers, you can do it that way. So what are the forces acting on the 6 kilogram mass? Get the obvious one. And is there more than one mass? I'm going to call this M1G. Because there's more than one mass. What else? Is there more than one normal force? Because there's more than one mass. I'm going to call it normal force number 1 to go with mass number 1. What else? Well, there's the force from the rope. What name did we give that? You're feeling it right now. Starts with the letter T. Yeah. That's what's pulling mass 1 to the right. Now, sometimes kids want to say, Mr. Dewick, isn't this 40 pulling on the 6? The 40's not touching the 6. 40's pulling on this, but not on this. What's causing this to accelerate is tension. Is there friction in this question? No, it says mu equals 0, so it's ice. Otherwise, if we had to, we could certainly add a friction force that way, but we don't need to. That's the free body diagram. 3 forces on mass 1. On mass 2, what are the forces acting on it? Get the obvious one. Is there more than one mass? I'm going to call it M2G. What else? I'll call it normal force number 2 to go with mass number 2. What else? Yep, that's what that 40 is. I'll draw an arrow and I'll just put an equals F. You could do a complete arrow and a 40 if you wanted to. And again, I should point out, technically this isn't a free body diagram because we didn't represent the masses as dots. We're labeling the forces on the picture that they gave us, but you've noticed that we've often just called that a free body diagram. We're missing one more. Which one? Because forces come in. Yep. If tension pulls on mass 1, tension pulls on mass 2. Which way do you think this is going to accelerate? Well, if it's going to accelerate at all, it's going to be to the right, because that's where I think I have an unbalanced force. So which way is the winning direction? To the? Good. We're going to write an equation, and our equation is going to be along the rope. That's very important, because those are the forces that are all in the same vector field, in the same, I can't quite call it direction, in the same plane. So, which way are we accelerating? Who's winning? Good. And now let's walk along the rope. Anything that's pointing to the right, we're going to, Alice, call it winner plus. Anything that's pointing to the left, we're going to call it loser minus. Okay? Winner. This tension here, winner or loser? Because it's pointing to the left, so minus. This tension here, winner or loser? Have we done all the forces along the rope? Yes. So equals, and then here was the tweak. We said instead of saying MA, if I have forces from more than one mass, I have to have more than one mass. Specifically, if I have forces from all of the masses, what did I write here? Do you remember from last year? M all times A. That was our tweak. Sienna, what do you help notice happens to the tensions? Oh, I love it when I lose tension. It's so relaxing. So everybody, if you want to, whenever you do these questions, you can take a little stretch, and then, you can lose some tension. Always good. Always good. Madison, what's part A asking me to find? How would I get the A by itself? So we're going to end up with this. A equals F applied divided by M all. How big was F applied as a number exactly? And M all, that's going to be mass 1 plus mass 2. It's going to be 6 plus 4. You know what, Madison? I bet you can do that in your head, because I think it's going to be 40 divided by 10. And I'll even show off, I'll go to 2 sig figs. Units, it's an acceleration. Good. I think what I said to you last year was something like this. To find the acceleration of everything, I write an equation for everything, all the masses. But to find an individual force, I'm going to look at an individual mass. How's that going to work? Well, Sienna, what does B want me to find? Why can't I use this equation to find tension? Okay? Here's my worst, best joke ever. Do you know why I can't use this equation? Because it has attention deficit disorder. It's missing tensions. It has a deficit of tensions. It has a tension deficit. Nothing? Okay, tough audience. Terrible joke, Mr. Dewick. So, Sienna, let's really quickly do the free body diagram. What did we have? We have M1G, normal force 1, and tension. Yes? Which way is mass 1 accelerating? To the, I'm looking for where it starts with the letter R. So which direction is winning? To the, who's winning? There's only one force pointing to the right. Who's losing? It's a trick question. Your equation ends up being tension equals, and because we're only looking at one mass, it's going to be M1A. You know what, Sienna? I bet you can do this in your head. What was M1 as a number exactly? What was A as a number exactly? How many newtons is tension? Yes. Wait a minute, Mr. Dewick. What if I found tension using the other mass? You know, it'd be really cool. It would be really cool if the tension we got from either mass was the same, and we could just pick whichever was the easiest one to find. That would be really, really cool. Let's see. Let's do a quick free body diagram for mass 2. We had M2G, normal force 2. We had F applied. We had tension. Sienna, which way is the 4 kilogram mass accelerating? Who's winning? Who's the loser? Madison, did you see it? I said, who's the loser? And she glanced at you. Oh, you can take her. Bonson Park after school. If I'm not there, just start without me. Fine. Who's the losing force? Tension. And we'll have this. You're getting all the jokes that I did with them last year, and I'm picking on you because they've all seen these jokes, and so they don't think they're funny anymore. And I'm hoping, you know how it goes, right? F applied minus tension equals, now it's just M2A because we're only writing an equation for that mass. I want to get the T by itself. What's right in front of the T, folks, that I don't like? And this is where I introduced you to that thing that a student had nicknamed the Swappy Dance, where we said, Mr. Dewick, why don't you plus that to that side, and at the same time, minus that to that side. And they end up just swapping positions. That's why I had a student nickname that the Swappy Dance. And so we end up with this. F applied minus M2A. And Sienna, instead of writing equals T, do you mind, can I write the T equals on this side? Because that's where we're used to seeing the thing by itself. How big was F applied as a number exactly, Sienna? How big was M2? What was A? It would be really cool if that worked out to 24 newtons. Does it? And so when you're finding the tension, I don't care which method you use, I usually pick the laziest method. Not always the easiest method. Sometimes there's a lazier method that requires me to do a bit more math in my head, but Zaina, I can do math in my head. Okay? What if we have more than 2 masses? What if we have 3 masses, or 4 masses, or 5 masses? We need to realize this first string is accelerating that mass. This second string is accelerating both masses. Really what we need to realize is if you have more than one string, you're going to have more than one tension. I'll call it tension 1 and tension 2. It's my high-tech system. We're going to start off the same way. Ooh, and there's friction. Free body diagram. I can handle this. I can do this. Claudie, what are the forces acting on the 3 kilogram mass? Get the obvious one. And is there more than one mass? I'm going to call this M1G. What else? Normal force number 1 to go with mass number 1. What else? Is there more than one rope in this question? So I'm going to call this tension 1. Do they want me to include friction? And I'm going to call it friction 1 to remind me that it goes with mass number 1. Easy notation. What about mass 2? Get the obvious one. Or as I like to say, M2G, because it's the mass that's changing, not gravity. Normal force number 2, yes. I guess we would have tension 1 this way, because forces come in pairs. What else? Is there another rope? Which way? To the tension 2. What else? There's one more thing. I got tension 2. Yeah. In fact, let's remember, there's going to be friction on all 3 of these. Let's not forget. Okay, and that's what I would have done as soon as I saw that. I would have made a mental note. Hey, do it. Make sure you put friction on all of these. Right? Friction, which way? To the left. And I'm going to call it friction force number 2. Number 2. And then it looks like for the third mass, we're going to have M3G. Normal force 3. And then I guess this 20 is going to be F applied. And now I got to make sure I don't forget anything. Definitely tension 2. Oh, and friction force 3. It's cluttered, but I can follow everything that's there. Okay? It wants me to find the acceleration of everything. I'm going to write an equation for everything. Which way is this thing accelerating, if it's accelerating at all? To the right. Good. Then who's winning? Yep. My equation is going to look like this. Winner. And now I'm going to walk along the rope. It looks like I have minus T2 plus T2 minus friction 3. Is that right? Go to the next mass. Minus T1 plus T1 minus friction 2. Go to the next mass. Oh, I think it's just minus friction 1. Is that all the forces along the rope? Now, there's always students that say, Mr. Dewick, where's mg? Why isn't mg? Mg is not along the rope. It's not showing up. Not going to show up. Did I get everything? This makes me winner minus loser plus winner minus loser plus winner minus loser minus, yeah, I think I got it. Oh, equals what? Yep. And this M all is going to be M1 plus M2 plus M3. Oh, this is a relaxing question. Losing lots of tension. How am I going to get the A by itself? I'm going to do that in my head, and on the next line, then I'm going to already start to write A equals. And I'm going to do a big fraction line, and it's going to be M1 plus M2 plus M3, right? M all. F applied is 20 minus F3, F friction 3. Friction is what times what? Mu times the normal force. So look up, don't write this down, but look up. In Physics 11, I probably would have told you to write down mu times normal force number 3. But in Physics 12, I think I can say to you, I don't know normal force number 3. Oh, but look. I don't know the force the same size as normal force number 3. Which one, Clody? I'm fine if you write mu M3G. And then it's going to be friction force number 2, mu times normal force number 2. I don't know normal force number 2. Oh, but look. I don't know the force the same size as normal force. What can I write? And I think it's going to be minus mu M1G. I'm running out of room. I would love to write in the numbers, because it's always nice when you're studying to know what we put in. But let's see if we can go straight to our calculator. Question? Right? There's my frictions. So it's going to be, I think I can do this in one step. Oh, on a test, I'd probably write out the numbers, and I'd give you enough room on a test. Bracket 20 minus, what's mu? I don't know what's mu with you. 0.2 times 5 times 9.8 minus 0.2 times 2 times 9.8 minus 0.2 times 3 times 9.8. Close off the top, divided by bracket 3 plus 2 plus 5. Whew! Did you get 0.04? This is barely accelerating. Friction is almost enough to keep this from accelerating. Okay. Cool. Alex, which mass would I avoid to find tension? Which mass looks the most cluttered with the most stuff on it? I'd avoid this one. Okay? I would only use mass 2 if the question specifically said, use mass 2 to find tension. I'm going to find tension 1 from this one. I'm going to find tension 2 from this one. So tension 1, look at it, Alex. Which way is mass 1 accelerating? Well, you know what? We can drop down the free body diagram here. So it was M1G, normal force 1, tension 1, friction 1. Right? Hand it in, and then you can continue from the notes where we are. Don't try and catch up. Just pick up where we are right now. That'll be easier. Alex, who's winning? Barely, but yeah, right? Because we're barely accelerating. Who's losing? So my equation is going to be tension 1 minus friction 1 equals M1A. How would I get the T by itself? Okay. And are we physics 12 now, Alex? I'm going to go M1A plus, instead of writing friction, I'm going to go mu times I don't know the normal force. Oh, but look. I don't know the force the same size as the normal force. I'm going to go plus mu M1G, and I could have lifted it right from here anyways, because I have it written right up there too as friction. Is that okay? So, M1 was 3, A was 0.04 plus 0.2 times 3 times 9.8. How big is tension? I have no idea here. You get, oh, wow, that's a fluke. 6 even? Okay. They usually won't work out evenly. That's a total fluke. I'll go 6.0, so it looks like I went to 2 sig figs. Jan, what's the next heading? What does it say? Chord what? Forget that. It's yucky. Let's do chord 3. I think that's going to be cleaner. So the free body diagram, I think we had this. M3G, normal force 3, F applied, and then we had friction force 3 and tension 2. Someone can double check me, but because I kind of went from memory, but I'm pretty sure that's right. Oh, by the way, Alex and Jen, in my homework, I probably wouldn't redraw the free body diagram. I think I'm good enough that just from this original, I could have just focused on mass 1, and I could have plucked that equation right there without having to isolate mass 1 and redraw. But if you have to, go ahead, right? And the same thing for mass 3. I probably could get it right from that free body diagram without having to redraw the mass 3. Who's winning? Who's the loser? Oh, Alex, did you see it? I said, who's the loser? He looked at you and he shook his head. You know what, Alex? We all know. You can take him. Bonson Park. Go right ahead. Okay? What's my equation, Jen? Tension 2. Yep. Yes. That equals M3A. Okay. What do I want to get by itself? Jan, what am I trying to find? Your hint is you're feeling some right now? Yeah. I think I'll do sort of a swappy dance. I'll plus the T2 over, because it's got a minus in front of it. I'll minus the M3A over, and the minus friction will stay where it is. So it's going to look like this. F applied, and then there's going to be a minus friction force 3 and a minus M3A. And you could have put those in any order. You could have gone minus M3A minus friction force 3 or vice versa. And if you don't mind, I'm going to put the T2 equals over on this side by itself where we're used to seeing it by itself. That should get us there. F applied was 20 minus, Alex, friction is what? Jan, friction is what times what? I don't know the normal force. Oh, but look, another force. I think it's going to be mu M3G. Let's see if we can go straight to numbers. On a test, I'd probably write out the letters, the algebra, on a test or a quiz, but let's pretend we're doing this on our homework. So we would go 0.2 times M3 times 9.8 minus 5 times, was 8.04, I think? Okay. Jan, let me know what you get. I might be able to do this in my head. Because 0.2 times 5 is 1, so it's going to be 20 take away 9.8, which is going to be 10.2 minus 0.2. Is it 10 even? I stuck the 0.0 so that I could go to 3 sig figs, because technically if you just write 10, how many sig figs is the number 10? Which is technically 1. So I'll go to 2 or 3. Is that okay? What? I think it's 0.04. They're barely accelerating. Yeah. What if we have a hanging mass and no F applied? Well, we need to realize what's causing this to accelerate is gravity acting on the hanging mass. No gravity, nothing's going to move. So, we're still going to do a free body diagram. It says identify the net force. Nick, you going to make it? Okay. Nick, let's do our free body diagram, you and I together, for here. It wants us to find the acceleration and it wants us to find the tension. Okay. What are the forces acting on this 2 kilogram mass? Get the obvious one. Is there more than one mass? Yeah. So I'll call this M1G. What else? And I'll call it normal force number 1 to go with mass number 1. What else? There's a rope. What else? Is there friction? How do I know? You're right. How do I know? They stuck a little mu in the picture. Okay? So, which way is this mass going to slide? So which way is friction going to point? Because friction resists motion. And I'm going to call it friction 1 to go with mass number. I think that's it. What are the forces acting on the second mass? Get the obvious one. I'll call it M2G. What else? Yep. Up. What else? Is there a normal force? No. The only way that would be is if it was sitting on a surface. It's not. Yeah, that's it. Okay? I wrote down here the net force accelerating the system. What's causing this to accelerate is M2G. That's what's causing this to go. Okay? Now, it's possible, Keegan, that friction in this direction could be bigger than M2G, in which case this will just be at rest. That's what happens if you hang something dangling off of a cliff and it doesn't accelerate down. If I'm a rock climber and I'm supporting my partner dangling down there, the friction between my feet better be bigger than my partner's MG. Otherwise, we're both going over. So it is possible to have friction be bigger. How would you find that out? When you solve for A, you'd get a negative A. Then you'd go, I've done something wonky, or I've got the wrong winner, is what it tells you. Meanwhile, Nick, let's see if we can come up with an equation Who's winning? And so what that means is anything that ends up pointing down once it gets here is going to be a winner plus. Anything that ends up pointing up once it gets to the bottom right, it's going to be loser minus. Can you write me an equation? I'll give you a hint. M2G. And again, we're going to walk along the rope. So what's the next one we run into, Nick? Winner or loser? We just decided down is winners, so this is going to be a... What about this tension? If you follow it, follow it, follow it. When it gets to this side, it's going to end up pointing down. So, yep, good. What about friction? Good. What about M1G? Does not go, it's not on the rope. It's not along the rope. Don't get tempted to stick it in here. That was a very common mistake kids made last year. That's it. Equals, Nick, do I have forces from more than one mass? Then I better have M all A. How you finding the crutches? They suck, don't they? You know what, Nick? Put your pencil down and stretch. You've earned a break. Lose some tension. Your shoulders are probably all sore. Your arms are probably all owie. Oh, lose a little tension, right? Right. Nick, how would I get the A by itself? By? Okay. So A is going to be M2G minus, and it's going to be all over M1 plus M2. There's M all. What can I write instead of friction force number 1? Friction is what times what? I don't know the force. Oh, but look. I think I can go mu M1G. You okay with that? And I'm kind of running out of room. Oh, no, wait a minute. I got way more room here. I didn't realize. I can keep going. A is going to be, I've scrolled down, Nick. What was M1? 4? Oh, it's right in front of me. Times 9.8 minus 0.4 times 2 times 9.8 all over 2 plus 4. Nick, my friend, what'd you get? Oh, there's a built-in error check anytime we have a hanging mass. Remember what it is? If we cut the rope, what's the maximum the acceleration could possibly be in free fall? I know this is going to be less than 9.8. If I get an answer bigger than 9.8, I've made a typo on my calculator. So there's a bit of a built-in error check that way. What'd you get, Nick? Anybody else? 5.2? Can you give it to me the 3 sig figs? 5 point what? 5.23? Meters per second squared. And you'll notice I'm being a bit casual. Acceleration is a vector. What's the direction? Well, it depends. You need to tell me which mass we're looking at. To the right or down. It could be positive or negative. And this is why we decided let's let positive be whatever makes the math easier, the winner. Did they also want us to find the tension, Nick? Good. Keegan, which mass would I use to find the tension? Look at your free body diagram. I've scrolled down. You gotta look at your stuff. Which mass would be easier to find tension with? I would use the hanging one. Less cluttered. So, what's my equation for the hanging mass? In other words, who's winning? Who's losing? Equals M2A. Swappy Dance, yes? And we'll get tension equals M2G minus M2A. The tension and the M2A would just swap places. What was M2 as a number? I've scrolled down, Keegan. What was it? 4? Times 9.8 minus 4 times, I'm going to write 5.23, but you're all going to use your answer button, right? What's the tension? 18.3? Is that right? Okay. Example 4. Mr. Dewick, example 4 is the same one we just did. It's got a curveball. Let's start out with our free body diagram. M1G, normal force number 1, friction number 1, tension, M2G, tension. Can anyone see what's the real tug of war between which two forces? Can you see it, Maddie? I'll give you a hint. One of them is M2G. Is M1G along the rope? That's a what? The tug of war is between M2G and friction. Okay? So now we're going to add one step further. Before I dive into this, on my calculator, on your calculator, really quickly, let's just crunch M2G. 4 times 9.8. What do you get? 39.2. Let's quickly crunch friction number 1. Friction number 1, friction, Lena, is what times what? Mu times the, I don't know the normal force. Oh, by the way, Maddie, this is where the M1G will show up inside the friction equation. It's going to be 0.4 times 12 times 9.8. What do you get? How big is friction? Who's winning? Zaina. Now, that doesn't mean that suddenly this box is going to start crawling to the left, magically lifting up that 4 kilogram mass, because inanimate objects don't work that way. What's really happening is everything here is at rest. This is stationary. This would be like a climber holding their partner, except the masses would be much larger. But it's the same concept where I've got more friction under my feet to hold my partner up so they don't slide down. I don't slide over with them on the cliff. So how would we have found that if we hadn't crunched this ahead of time? You would have got a negative acceleration. If you're ever doing a multiple mass question, and you get a negative acceleration, go look at your individual forces. You probably picked the wrong winner. Okay? So here, find the acceleration of the system. Let's make a little note. Friction was how big? 47.04. M2G was 39.2. So, is 0. And again, Lily, if you didn't catch that because you didn't check it out ahead of time, by the way, the reason I didn't check this one out ahead of time, this mass is smaller than that mass. Friction is going to be smaller. I got suspicious when this mass was so many times bigger here. I got worried. I better check that out. If you're looking for a rule of thumb, Madison, I just compared the masses. That's such a heavy mass. I don't know if the 4 is going to pull it off the cliff. What's tension? Which mass would I use to find tension? It's cleaner, and it's going to be this. Who's winning? Well, sort of gravity minus tension equals, what's the acceleration exactly as a number? Or, you know what I could have said since we're not accelerating? It's a tie. No winner. If I was really clever, I could have said, you know how big tension is? It's that big. It's going to be 39.2 newtons. I didn't even bother retyping it. I noticed, hey, I have M2G sitting there. So that's a habit or a skill you can add to your arsenal, Zaina, especially if you notice that one mass is significantly larger than the other one. Do your free body diagram. Quickly, on your calculator, without writing anything down, crunch the forces, do a quick comparison, and you can tell ahead of time if you're going to pick the wrong winner. But if you miss it, how would you know? When you solve for A, your calculator would tell you that A was what? Negative. Negative. And that means go check, you picked the wrong winner. Doesn't mean that it's accelerating necessarily in the opposite direction. All it means is you picked the wrong winner. Now go analyze the situation. Sometimes you will be accelerating in the other direction if it's a complicated system, but not like this. Example 5. Last one and we're done. It says, find the coefficient of friction required for this system to accelerate at 5.5 meters per second squared. Okay. Any thoughts on how I might want to start out? Zaina, you done yawning? How should I start out? Free body diagram, that's what you said, right? Yeah, okay. M1G, normal force 1, tension. Is there friction? There must be, because they're asking me to find the coefficient of friction. So, friction force number 1, M2G, tension. Who's winning? Well, they're telling me it's accelerating. I'm going to assume it's accelerating down and over the cliff because that's what makes sense. So I think my equation is going to be M2G minus T plus T minus friction equals M all A. Cohen, how'd the test go? Okay. Need you to lose a little tension? Because if you need to lose a little tension, I give you permission to just stretch it out if you want to. Now, normally we would say, divide by M, but what are they asking me to find here? What are they asking me to find here? Where is the mu, where is the coefficient of friction hidden inside of? It's hidden inside of here. So I think the first thing I'm going to do, Lily, is Swappy Dance, get friction by itself. It's going to be M2G minus M all A equals... Oh, and you know what you said? What did you say, Lily? Mu times the normal... I don't know normal force number 1. Oh, but look. I know the force the same size as normal force number 1. What? M1G. You'll notice, Mallory, I'm skipping step. In Physics 11, we would have written every one of those steps out. I'm saying now, as far as I'm concerned, if you're comfortable, cut some corners. On a test, I'd probably show every step, but this isn't a test. Oh, Mallory, how would I get the mu by itself? I don't feel like rewriting this, so I'm just going to go like that. And in fact, I'm going to say, go to your calculators and see if you can do this. M2, 4 times 9.8 minus, I guess it's going to be 2 plus 4 in brackets. You could do that in your head, 6, but if it wasn't, times 5.5. There's M all, A. Close off the top, divided by bracket, 2 times 9.8. Oh, typo, Mr. Duke. And I get a coefficient of friction of 0.316? Yep. Units. None. Okay, it's a unitless, dimensionless ratio. My point, Keegan, is as far as I'm concerned now, for many mass problems, I can ask you to find anything once you have the equation set up. If I give you the acceleration, I could have you find the mu. I could have you find one of the missing masses. We'll talk about that a bit more tomorrow, but anything is fair game. Is that all right? And that's one of the reasons I really pressed that formula manipulation on you last year, so I don't need to show you every variation of every situation. Okay? What's your homework? In number 1, 2, 3, and 4, there's no friction. That's too easy. Let's skip them. 5, there's no friction. I'll do number 6. I'll do 1 with no friction as a hanging mass. But now 7, there's friction. 8, there's friction. That's good. Number 8 and number 9. Ooh. What's the mass here in number 9? 4. Will it accelerate? Well, I guess it will because I gave you the answer. You know what? 8 and 9 are the same question. I'm going to skip. If you got 8 wrong, do 9, but otherwise you can skip 9. 11. Did they want you to find the tension in number 11? No, just find the acceleration. So all you're going to do is write the main equation. 12, please notice in number 12, the boxes are made from different materials, so you'll have a different mu for each mass when you find friction. Yeah, that's more realistic. There's a 12. That's why it has a 12. So the one that has a 1 followed by a 2 and a period, we'll decide we'll call that one number 12. Is that okay with you? Okay. 13. 13's a little tricky, but see if you can figure it out. I'll skip 14. I'll skip 15. We'll talk about missing masses tomorrow. That's enough. You got 15 minutes to work on this. I think you can probably get this done in class. There's probably, for most of these, enough room if you write beside. You can show your work next to the diagram, or you can do these on a separate piece of paper. I don't care. Whatever works better for you.